Okay, so this is circuits that have capacitors in them only. The reason why I'm saying that is because we can get into much more complicated circuits that have both resistors and capacitors. We're not there yet, so we're just going to focus on simply circuits with capacitors. We've already done circuits with resistors, and so this is the next step. Now, one thing that's really nice about these circuits with capacitors in it is they are exactly opposite of how we added resistors. So when we added resistors in parallel, we added the inverses. When we added resistors in series, we added them just the sum of them. In capacitors, it's opposite. So in parallel, we just sum up all the capacitors. So if I have a picture like this where I've got 1, 2, 3 different capacitors, all I've got to do is add up the values of those capacitors. Now, the reasoning behind it. Each capacitor is going to gain a certain amount of charge, Q. Okay? The voltage across each one has to be the same. So if I have this relationship that says Q equals CV, you'll notice that the capacitance times the voltage, the equivalent capacitance times the voltage, is going to give us our total amount of charge. So if I'm summing up all the charges, that would be equal to the total capacitance times the voltage. Okay, so we've got simple sum equation for capacitors in parallel. If I come down here and look at the series version, okay, we're going to end up adding the inverse of it. Okay, and here's why. The charge on each one of these is going to be the same, and this is the reasoning. There's only one path for the electrons to go. Okay, so when we flip the switch and the battery comes on, you're going to build up a certain amount of negative charge here. Whatever this negative charge is, based on conservation of charge, limits how much positive charge can be built up here. Well, if a certain amount of positive charge builds up here, you're going to get the same amount of negative charge there. And if there's this amount of negative charge, you're going to get the same amount of positive charge here, and so on and so forth. So this total charge across each one, the total charge is going to be exactly the same. Now, the sum of all the voltages on them must add up to equal the total voltage. So if I add all the voltages, okay, and I have a common charge, then the equivalent capacitance is on the bottom of this particular equation. Therefore, when I add capacitors in series, I have to add the inverses, just like we did with the resistors in parallel. Now, when we did stuff with the resistors, and we ended up finding the voltages and the currents through each resistor. In these circuits, what we're going to do, and we'll do some examples tomorrow, is we're going to find the charge and the voltage. Now we used to use V equals IR. Now we're going to use Q equals CV. This is our little basic definition of capacitance. Okay?